Good morning students, welcome to Witsconnect. Already yesterday we have discussed about the half-wave rectifier ripple factor calculation, and we have seen about the different definitions like efficiency, peak inverse voltage, form factor, peak factor. So those are the yesterday's topics. So today we are going to discuss about the full wave rectifier circuit. So this is the circuit of the full wave rectifier. So this is the input voltage we are giving at the center tap transformer. Here we are using center tapping transformer. Why we have to named it as center tapping? The center terminal of the secondary terminal transistor. The secondary terminals of the center terminal transistor is connected to the load resistor. That's why we named it as center tapped full wave rectifier. Okay, so here we are using two diodes, D1 and D2, and at the load resistor we are getting the output voltage, and these are the input voltage or AC input voltage, and this is the output signal. This is the pulsating DC output. The output is pulsating DC output. So in full wave rectifier, so it converts AC voltage into pulsating DC voltage. Okay, so in full wave rectifier what is happening? It converts the AC voltage, input AC voltage into pulsating DC voltage. Okay, so here in full wave rectifier the rectifier uses two half cycles, both half cycles. Okay, now in full wave rectifier what is happening? The rectifier uses positive and negative half cycles. Okay, now that's why we named it as full wave rectifier. So here coming to the operation of full wave rectifier. So during positive half cycle what is happening? The transformer secondary terminal, this is the positive half cycle. During positive half cycle what is happening? The transformer secondary terminal A becomes positive, B becomes negative. So that the diode D1 is going to be forward biased and diode D2 is in reverse bias. That means the anode terminal of the diode 1 is in forward bias and diode D2 is said to be reverse bias. So the current conduction takes place only in diode D1. So there is a voltage drop across the load resistor RL. So you will get the output voltage across the load resistor RL. This is the output. So whatever the input voltage we are giving, it will directly goes to the load resistor RL. So like that, during negative half cycle, what is happening? The transformer secondary terminal A becomes negative, B becomes positive. So what is happening here? The diode D1 now it is in reverse biased mode and diode D2 in forward biased mode. The current flows only in diode D2 and the output voltage will be at load resistor RL. So negative half cycle, here it will comes like this. Okay now, so here in both half cycles the current conduction takes place in the load resistor RL. That's why we named it as full wave rectifier. So this is the operation of full wave rectifier, and here in full wave rectifier the input AC voltage is converted into pulsating DC voltage. This is the pulsating DC voltage. So this is the construction and operation of full wave rectifier. So coming to the calculation of ripple factor, what is the ripple factor formula? Under root Vrms by Vdc whole square minus 1. Okay now, so here to calculate the ripple factor, the average voltage or DC voltage available across the load resistance is, you have to calculate Vdc and IDC. So Vdc equal to what? You can write 1 by pi integral 0 to pi Vm sin omega t d omega t. Sine wave form kabatti sin omega t తీసుకున్నాను with respect to the d omega t. So within the interval 0 to pi for first positive cycle. Okay na? So this is the output kada, pulsating DC output 0 to pi varaki. Okay na? 0 to pi Vm maximum voltage enta diniki Vm kada plus Vm. So it is Vm sin omega t d omega t. So Vm is constant kabatti Vm munduku rasaru Vm by pi. So if you integrate sin omega t, it is minus cos omega t. Integrals are 0 to pi. So if you apply the limits and if you calculate, you will get 2 Vm by pi. So this is the DC voltage. Vdc equal to what? 2 Vm by pi. So like that IDC equal to Vdc by RL. That is the formula. If you substitute Vdc here, 2 Vm by pi into RL. It is equal to what? So 2Im, it is equal to 2Im by pi. Okay na? So where it is equal to 2Im by pi, and IRMS equal to Im by root 2 vastadi. Okay na? So IDC equal to 2Im by pi and IRMS equal to Im by root 2. Im ante enti manaki ikkada actual ga maximum current. Okay na? So if the diode forward resistance RF and the transformer secondary winding resistance RS are included, we can write down the equation of VDC. Actually VDC equal to enti 2Vm by pi. So you can write like this, it is equal to IDC into RS plus RF plus RL. So RS ante series resistance, RF ante forward resistance plus RL. So this is VDC. So from this you can write the equation for IDC. IDC equal to ఏమవుతుంది? IDC equal to what? IDC equal to దీన్ని తీసుకురండి, ఇది కిందికి వస్తుంది. సో IDC equal to VDC by RS plus RF plus RL. ఓకేనా? సో VDC అంటే యాక్చువల్గా ఏంటి మనకి 2Vm by pi సబ్స్టిట్యూట్ చేయండి. సో 2Vm by pi into RS plus RF plus RL వస్తుంది. సో RMS value of the voltage at the resistance is VRMS equal to what? Root mean square. ఎలా వస్తుంది? VRMS equal to root, ఇది mean అంటే 1 by pi, square అంటే Vm square sin square. So with respect to the intervals between 0 to pi. So it is equal to under root 1 by pi integral 0 to pi Vm square sin square omega t into dt d omega t. So ఇది మీరు క్యాలిక్యులేట్ చేస్తే you will get Vm by root 2 వస్తుంది. Okay na? If you integrate and if you calculate, you will get Vm by root 2. So now you have to calculate the ripple factor. What is the ripple factor? VRMS ఎంత వచ్చింది మనకి? Vm by root 2 వచ్చింది. VDC ఎంత వచ్చింది మనకి? 2Vm by pi. So Vm get cancelled and you will get, if you calculate this, you will get 0.48. So this is the ripple factor of full wave rectifier. It is about 0.482. Coming to the half wave rectifier, it is about ఎంత వచ్చింది మనకి నిన్న? 1.21. Okay na? Half wave rectifier ripple factor value is 1.21. So full wave rectifier కి వచ్చేసరికి ఏమైంది? ripple factor తగ్గిపోయింది. Okay na? Compulsory ripple factor it should be in low value. Okay na? So that you will get approximately DC output. Okay na? So compulsory the ripple factor value will be as small as possible. Okay na? So it is very small, the small amount of value you will get in full wave rectifier. So you at the output you will get approximately DC output. Okay na? This is about the ripple factor calculation of full wave. Coming to the efficiency of the full wave rectifier, it is the ratio of DC output power to the AC input power, that is equal to PDC by PAC. So DC output power, PDC it is equal to VDC whole square by RL and PAC equal to VRMS whole square by RL. So VDC formula for full wave rectifier, DC voltage is 2Vm by pi. So it is whole square here. VRMS for full wave rectifier, it is Vm by root 2. Formula already derive chesamu. So here Vm is going to be cancelled. You will get 8 by pi square. If you calculate this in terms of percentage, you will get 81.2%. Okay na? So what is the efficiency of half wave rectifier? It is 40.6%. For half wave rectifier, the efficiency is 40.6%. Coming to the full wave rectifier, it is double. Why we are using 2 diodes na? In full wave rectifier, you are using 2 diodes. That means the efficiency is going to be double. It is about 81.2%. So this is about the efficiency of the full wave rectifier. It is 81.2%. So therefore, the maximum efficiency of full wave rectifier is 81.2%. Coming to the TUF means transformer utilization factor. So coming to the efficiency of the full wave rectifier, it is defined as the ratio of DC output power to the AC input power. So it is equal to PDC by PAC. So PDC formula enti? VDC whole square by RL, PAC equal to VRMS whole square by RL. So coming to the VDC, DC voltage for full wave rectifier formula is 2Vm by pi and VRMS it is Vm by root 2. Vm get cancelled. If you calculate this, you will get 81.2%. So therefore, the maximum efficiency of full wave rectifier is 81.2%. Coming to the efficiency of half wave rectifier, it is 40.6%. So here it is doubled. Why? Because in full wave rectifier we are using 2 diodes. So that means it is doubled of the half wave rectifier. It is 81.2%. So coming to the transformer utilization factor, it is defined as the average transformer utilization factor in a full wave rectifier circuit is determined by considering the primary and secondary windings separately, and it gives a value of 0.693. Okay, so coming to the form factor, it is the ratio of RMS value of the output voltage by average value of the output voltage. RMS value of the output voltage means VRMS. VRMS it is nothing but Vm by root 2. Average value means DC voltage. So VDC equal to 2 Vm by pi, that is for full wave rectifier. So Vm get cancelled, you will get pi by root 2, it is about 1.11. That is the form factor of the full wave rectifier, you got 1.11. So coming to the peak factor, it is the ratio of peak value of the output voltage. It is indicated by Vm. Maximum value or peak value of output voltage, it is indicated by Vm. RMS value of the output voltage. VRMS equal to what? What is the formula for full wave rectifier? Vm by root 2. So Vm get cancelled, you will get root 2. Okay na? So coming to the peak inverse voltage. How will you define the peak inverse voltage? The maximum reverse voltage. The maximum reverse voltage that a diode can withstand without any destroying of the junction. Okay na? Okay, now that is defined as peak inverse voltage. It is 2 Vm for full wave rectifier. So, and peak inverse voltage for half wave rectifier, it is Vm. Okay, now this is for half wave rectifier and this is for full wave rectifier. Okay, next topic is bridge rectifier. So here this is the circuit diagram of bridge rectifier, and this is the input and output waveforms of the bridge rectifier. So if you take the bridge rectifier, the need for center tapped transformer is eliminated by using this bridge rectifier. Okay, so here we are using 4 diodes, D1, D2, D3, D4. They are connected in the form of a bridge. Okay na? So, and these are the primary terminals of this step down transformer, and these are the secondary terminals of this step down transformer. At the primary terminals we are applying the AC input voltage. This is the AC input voltage with maximum voltage Vm, and this is the positive half cycle, negative half cycle. Okay, so and the secondary terminals are connected to the diagonal elements. You are connected like this, diagonal elements of the bridge form. Okay na? And other two ends of the bridge rectifier circuit is connected to the load resistor. So these 2 diagonal ends are connected to the AC input, and other 2 inputs are connected to the load resistor RL. So this is the construction of the bridge rectifier. At the load resistor RL we are taking the output voltage. Okay, so coming to the operation of the bridge rectifier, during positive half cycle of the AC input voltage. During positive half cycle of the AC input voltage, diodes D1 and D3, here it will get positive and it will get negative. That means here the D1 and D3 diodes are forward bias, that means D1, D3 diodes conducts, and D2, D4 diodes are reverse bias, that means D2, D4 diodes will not conduct. So here the D1, D3 diodes will be in series with respect to the load resistor RL. So whatever the input AC voltage you are connecting, it will appear at the load resistor RL like this. So during negative half cycle, what will happening? The transformer secondary terminals becomes negative and positive here. So in this stage, diodes D2 and D4 are in forward bias, D1 and D3 are in reverse bias. So D1, D2 and D4 diodes only conducts. So D2 and D4 diodes lo maatrame current anedi flow avutundi. So in D1, D3 diodes lo it doesn't conduct. There is no flow of current through the diodes D1 and D3, and here D2 and D4 diodes are in series with the load resistor RL. So whatever you are applying the negative half cycle, it will gets like this. So the output is, if you are applying bidirectional input, it will appears as a unidirectional way. So this is the pulsating DC output voltage of the bridge rectifier. So this is the operation. So coming to the bridge rectifier, the average voltage VDC and average current load current IDC are same as the full wave rectifier. So what is the equation for VDC? VDC equal to 2 Vm by pi and IDC equal to Im by pi. Okay, 2 Im by pi. IDC equal to 2 Im by pi. Okay, these are the equations of the VDC and IDC. So bridge rectifier ki kuda same ive equations. Okay na? So same as full wave rectifier VDC equation and IDC equation. Coming to the maximum efficiency of the bridge rectifier. Maximum efficiency of the bridge rectifier, it is 81.2%, same as full wave rectifier, and peak inverse voltage it is Vm. For the bridge rectifier, peak inverse voltage it is maximum voltage Vm. So this is the construction, operation and the VDC value, IDC value and efficiency, peak inverse voltage of the bridge rectifier.